Okay, the next same for condition for propagation or expression for numerical aperture in optical fiber. An optical fiber, okay. So, when a ray of light will incident inside the optical fiber, then the complete total reflection will takes place for the angle of incidence, which is lesser than, which is greater than the critical angle and lesser than the acceptance angle. So, that we get to know. Now, we have to derive the condition for this optical fiber. What is the condition to travel light inside the optical fiber? So, for that our expression for numerical aperture. Numerical aperture means what is, how much the light will gather inside the optical fiber. What is the capacity of this optical fiber to collect the number of rays. So, that what is the condition required. So, that we have to derive. Okay. So, for that we have to apply the Snell's law. We know the how to apply Snell's law, that is from other medium to the next from rarer medium to the denser medium. So, that we have to. First let consider a naught. So, this is the surrounding medium. So, we refractive index of the surrounding medium, N1 the refractive index of the denser medium, and N2 the refractive index of the rarer medium. So, then we have to apply the Snell's law at point A. Okay. First let N0, N1 and N3, N1, N2 are the refractive index of surrounding medium. The surrounding medium, core and cladding. So, N1 and N2. So, next we have to apply the Snell's law at point A. Okay. So, if we apply the Snell's law at point A, so from where the ray of light is incidenting and how the ray of light is reflecting. So, first apply Snell's law at point A. At point A, then what we will get? So, first refractive index surrounding medium, and what is the angle it is forming, that is sin theta naught in surrounding medium. Then of the ray of light when incidenting inside the optical fiber, so that is core. So, the refractive index is N1 and what is the angle it is making, so that is sin of theta 1, sin theta 1. So, this is at point A. Then similarly apply the Snell's law at point B next. Now, apply the Snell's law at point B. So, now the ray of light from where it is entered, from the refractive index of the medium N2, and what is the angle it is forming, 90 minus theta, sin of 90 minus theta 1, and is equal to the ray of light, it is interfaces between. So, now apply the Snell's law at point B. So, now the ray of light is from a core itself. So, that is why N1 sin of, and what is the angle it is forming at point B is 90 minus theta 1. So, that is why sin of 90 minus theta 1 and is equal to the ray of light is passing through cladding. So, that is why N2 sin of, and what is the angle it is forming when it is when the ray of light is interfacing between the two medium. So, with the angle of refraction theta r, but the angle of refraction at that point, so theta r is equal to 90 degree. So the angle of refraction at that point is theta r is equal to 90 degree. So we will get sine of 90 minus theta, sine of 90 minus theta. So that is in first quadrant. Sine of 90 minus theta 1 is equal to, we know that cos theta 1. For 90 and 270, sine will become cos, cos will become sine, and so that will give n1 cos theta 1 is equal to n2 theta r is equal to 90 degree. So sine 90 degree value is equal to 1. So that's why we will get n2. So write in terms of cos theta 1, then we will get cos theta 1 is equal to n2 by n1. Okay. So name it as equation 2. So that is sine of 90 minus theta 1. In first quadrant all are this positive only. So but for 90 and 270 will change. Sine of 90 minus theta 1 will become cos theta 1. Okay, so that's why we will get cos theta 1 is equal to n2 by n1. So just we have to first you have to know how the Snell's law I have to apply at the point A, and what is the Snell's law it will give at point B. We have to observe from where the ray of light is entering, from which medium, and what is the angle it is forming. So initially it is entering from surrounding medium, but it making an angle with the optical axis, that is theta naught. So that's why n naught sin theta naught, and next that is equal to the ray of light is entering into the core, that refractive index is n1 and it is making an angle theta 1. So that's why n naught sin theta naught is equal to n1. So similarly at point B, at point B here the ray of light is in core only, so refractive index n1. So that's why n1, and what is the angle it is making? 90 minus theta 1, sine of 90 minus theta 1, that is equal to, in the ray of light that is entering in between the interface of core and cladding. So that's why n2, and making an angle of sin theta r. So therefore, but the sin theta, what is the refraction angle here? 90 degree. So we will get into sin theta, sin 90 is equal to 1. But sine of 90 minus theta 1, in first quadrant all are positive, but sine will become for 90 and 70, sine will become cos and cos will become sine. So that's why here sine of 90 minus theta 1 will give cos theta 1. So I name it as equation 2. So just again now we have to make the rearrangement of equation 1. Okay. So then we have to, if we make the rearrangement of equation 1, that is in terms of sin theta 1, and we know cos square plus theta plus sin square theta is equal to 1. From that we have to get the sin theta 1. So now just substitute this in above equation, then what we will get, substituting in above equation, we get root of 1 minus square cos square theta 1 is equal to n naught sin theta naught by n1. Okay. So but root of 1 minus cos square theta 1 is root 1 cos theta value we know. So substitute equation 2. Substitute equation 2. So then we get root of, so 1 minus cos square theta is n2 square minus divided by n1 is equal to n naught sin theta naught divided by n1. Okay. So if we rearrange this, then what we will get, write again that equation here. n1 square minus n2 square divided by n1 square. So if we take this n1 outside, then square root and square will get cancelled. So we will get root of n1 square minus n2 square divided by n1, and here n0 sin theta naught divided by n1. So this n1 will get cancelled, then we will get sin theta naught is equal to root of n1 square minus n2 square divided by n0. So this is the expression, one expression. But what is the condition for this, the ray of light to work? So that is the angle of incidence, the theta naught is greater than, and if we can, this is if this optical fiber placed in the surrounding medium, that is in air, if a naught is equal to 1, then what we will get, sin theta naught is equal to root of n1 square minus n2 square. So that is sin theta naught when we used to place, if a naught is equal to 1, that is in surrounding medium. If the surrounding medium is air, the surrounding medium is air, then sin theta naught is equal to root of n1 square minus n. So, but the condition is what, to propagate a light inside the optical fiber. This we can write sin theta naught in terms of acceptance angle. So that is, so sin theta naught is also, we can write is numerical aperture is equal to root of n1 square minus n2 square. Okay, like this also is to write, that is in terms of numerical aperture, where sin theta naught means n of a numerical aperture. So this numerical acceptance angle, we can write this sin theta naught is equal to root of n1 square minus n2 square. Also theta naught is equal to sin inverse of root of n1 square minus n2 square. So this is the acceptance angle. Theta naught is equal to sin inverse of. So acceptance angle is nothing but it is the maximum angle at which the ray of light will propagate inside the optical fiber. That is with the sin inverse of square root of refractive index of core square minus the refractive index of the cladding. So what are acceptance angles is the sign of maximum angle at which the square of rate, the sign of maximum angle at which the ray of light is guided inside the optical fiber with the square root of differences of core and cladding square is nothing but acceptance angle. And what is numerical aperture? So that numerical aperture means it is the collection of the ray of light. So numerical aperture is the maximum angle at which the ray of light will be gathered inside the optical. It is a measure of the efficiency of the optical fiber, is nothing but numerical aperture. Okay. So then what is the condition for this? If theta I is the angle of incidence, theta I is angle of incidence, then theta naught is the acceptance angle. So condition is, so that is when theta I, the light to propagate inside the optical fiber, that is theta naught is greater than theta I. So apply the sign on both sides, then we get sin theta naught is equal to sin theta I, but the sin theta naught value is what? Root of n1 square minus n2 square. Root of n1 square minus n2 square is greater. So this is nothing but numerical aperture. So the numerical aperture is greater than the sign of angle of incidence. So this is the condition for the propagation of light. Condition. Okay. So this is the main condition for the propagation of light inside the optical fiber. So totally the numerical aperture, it measures the efficiency of the optical fiber, how much light ray can gather inside the optical fiber. So this is about the condition of the numerical aperture. So whether they can ask what is the expression for numerical aperture, so or else condition. So then we have to derive by this. So sin theta I is less than numerical. So what is the condition for propagation of light in optical fiber is sin theta I is less than numerical aperture. So what is numerical aperture? So totally it is the measure of the efficiency of the optical fiber, collection of the number of light rays in the optical fiber. So it is a measure of the power launching efficiency or collecting of the light rays inside the optical fiber. How much light rays can collect inside the optical fiber. So that is nothing but numerical aperture. So numerical aperture is nothing but it is a measure of or collecting of ray of lights. So totally numerical aperture means it is a measure of the power launching efficiency or collecting of ray of light inside the optical fiber. How much light rays can gather inside the optical fiber. So that is nothing but the numerical aperture. So and then acceptance angle. So that numerical aperture, what is represented by numerical aperture is equal to root of n1 square minus n2 square, and it is also defined as the square root of the difference of the squares of refractive index of core and cladding, numerical aperture. And acceptance angle, it is the maximum angle to the this is the acceptance angle, theta naught is the acceptance angle. So it is the maximum angle to the optical axis at which the ray of light will propagate inside the optical fiber. So that is nothing but acceptance angle. So it is the maximum angle. So it is the maximum angle to the optic axis at which ray of light propagates. Light enters the So it is the maximum angle to the optical axis at which ray of light enters the optical fiber, to propagate. So that is to run nothing but acceptance angle. So that how we used to represent theta naught is equal to sine inverse of root of n1 square minus n2 square. So to find out the acceptance angle, that is equal to sine inverse of root of n1 square minus n2 square. Then critical angle. What is the critical angle? So that when we used to apply the Snell's law at point B, so then what we used to get? The ray of light is entering from the core. So n1 sine of theta c. So, this 90 minus theta 1 is nothing but critical angle. So, we can write that as theta c. So, n1 sin theta c is equal to n2 sin theta r. So, from this we can write it as sin theta c is equal to sin theta c is equal to n, but the angle of refraction theta r is equal to 90 degree. So, sin 90 degree is equal to 1. So, that is why this will become n2 and n2 by n1. So, this will give theta c is equal to sin inverse of n2 by n1, n2 by n1. So, what is the critical angle is nothing but sin inverse of n2 by n1. At the maximum angle of sin inverse of the ratio of the refractive index of the cladding to the core. So, this is the critical angle. Okay. So, this critical angle, acceptance angle and numerical aperture. So, fractional index change is nothing but it is the ratio of the difference between the core and cladding to the refractive index of the core. Refractive index difference between the core and cladding to the core. So, the fractional index change is nothing but that is the difference between the refractive index of the core and cladding to the refractive index of the core. So, this is the fractional index change. Okay. So, the next is V number. Okay. So, V number means that is it is a parameter. It is used to measure the number of light rays can enter inside the optical fiber. How much the light rays it can sustain inside the optical fiber. To measure that, this V number parameter is required. So, that is depending upon the wavelength of the optical fiber and the diameter. So, depending upon that, so this V number parameter is defined. So, therefore, that is defined by V is equal to pi d divided by lambda of differences of refractive index of core and cladding. So, this is the formula for this V number, where d is the diameter, and lambda is the wavelength of the light ray which is travelling inside the optical fiber. So, light ray travelling inside the optical fiber. So, the number of modes that we used to represent it by a n. So, the number of modes propagated inside the optical fiber is measured by the parameter, that is V number. Number of modes is nothing but the number of rays. So, where d is the diameter of the core, because depending mainly upon the diameter of core, and which is the lambda is the light propagating inside, and n1 n2 is nothing but we know refractive index of the core and cladding. So, suppose if V is very greater than 1. So, in this V, if V is very greater than 1, then is very greater than 1, then the number of modes is supported inside the optical fiber. So that is to represented by n is equal to v square by 2 to calculate the number of modes. So that is where n is the number of modes, n is equal to v square by 2, v is the parameter. So there is no unit for this. So like this we can calculate the number of modes can propagate inside the optical fiber. Thank you.